Welcome to day 7. Today's topic is energy involved in covalent bonding. All right, so bonds result from the tendency of a system to seek its lowest possible energy, and a collection of atoms is generally more stable than separate atoms. So just keep in mind, we're always going to take the perspective of the system, and if we push a ball uphill, the system is going to gain energy. It's going to be less stable. That's an endothermic change. And if that ball rolls downhill, it will be more stable and it will release energy in the form of an exothermic change. All right, so let's take the perspective of some molecules. Maybe we have some O2 and maybe we have some methane. And these atoms are more stable in the form of molecules than they are all by themselves. So just remember, as we go up higher, there's going to be higher energy. So these molecules are somewhat stable, more stable than if they were individual atoms. Now, what we can do is we can break those bonds, and breaking bonds is an endothermic change. So we have to put energy in to break these bonds. The energy of the system is going to increase. So now we have all these separate atoms. We've got these oxygen atoms and carbon atoms and hydrogen atoms up here, and they are less stable as individual atoms than they were as a molecule, whether that's oxygen molecules or methane molecules. So going from here to here, this was an endothermic change. Now, because nature kind of seeks the most stable configuration, realistically what's going to happen is that these atoms are going to recombine in such a manner that they are more stable. And probably what we're going to end up with is going to be some water molecules and some carbon dioxide molecules. If you know anything about combustion, those are likely products. So we started off with some molecules of methane and oxygen that were somewhat stable. We broke those chemical bonds and we created a less stable situation. But then in the long run, when those atoms reconfigured into a more stable configuration, we got the release of energy and we ended up with much more stable molecules than we began with. And those molecules were carbon dioxide and water. All right, so let's take a look at methane. Methane is a molecule. It has carbon in the middle and four hydrogens. It's in the shape of a tetrahedron. And if you wanted to break one individual bond, it would take about 413 kilojoules to do that if you had a mole of methane molecules. But methane doesn't have one bond, it has four identical bonds, four identical carbon hydrogen single bonds. So breaking all the bonds in a methane molecule would require the input of 1652 kilojoules for a mole. But on the flip side, if you were to make a mole times 4 bonds of carbon and hydrogen, it would release 1652 kilojoules of energy. So breaking a bond requires energy. That would be endothermic, and making a bond is exothermic. It's going to release energy. So one carbon-hydrogen bond is going to take 413 kilojoules per mole of molecules to break. Okay, let's look at a different molecule. Let's look at one that's very similar, and this is chloromethane, or methyl chloride gas. So very similar to methane in that one of those hydrogens has been replaced with a chlorine. So still a tetrahedral molecule. So we know that each one of those carbon-hydrogen bonds is 413 kilojoules per mole. And if it takes 1578 kilojoules to break all the bonds, we could kind of work our way backwards and say, how much energy does it take to break one carbon-chlorine bond? And looks like one carbon-chlorine bond would take about 339 kilojoules to break. So we have three carbon-hydrogen bonds, each one at about 413 kilojoules per mole, and we have one carbon-chlorine bond at about 339 kilojoules per mole. So if you wanted to figure out how much energy it would take to break all these bonds, you basically do a little bit of math and say 3 times 413, that's kilojoules per mole, and 1 times 339, that would also be kilojoules per mole, and if you added that up, it should add up to 1578, and of course the unit would be the kilojoule per the mole. All right, another example here. All right, so bonding is used to explain molecular stability. Some molecules are obviously more stable than other. If we understand how much energy it takes to break a bond, we can also figure out how much energy will be released when a new bond is made. And this is really the principle that governs, how we do chemistry. If it's an exothermic reaction, it's more likely to be spontaneous. If it's an endothermic reaction, we're more likely to have to add energy. So, guys, there are a few problems in the book. You can check the back of the chapter. The example and the assignment today is very similar to one of the problems in the back of the book. Remember, you can always shoot me an email, or you can ask a class comment on Google Classroom. All right, guys, this might be the last lesson before spring break. I miss you guys. I love you guys, and I'll talk to you in about a week.